Let's go through the process of graphing a rational function. Here we have example of a function, x plus 2 over x squared minus 4. So what should we do first in preparation for graphing? Well, we should actually factor each numerator and denominator, so that will be the first step. In this case, the denominator is x minus 2, x plus 2. And this will help us to find the domain of the function. So the domain of this particular function f is all real numbers, but we can't have 2 or negative 2. So take away 2 and negative 2. Next, we can look at common factors of the numerator and denominator. There is one common factor, x plus 2. These common factors can be actually reduced, but we need to remember that the roots of those common factors, in this case negative 2, produce a hole in a graph. So we have one hole at negative 2. The following step would be to find all asymptotes and graph them using dashed lines. So our simplified function is 1 over x minus 2. Since we have denominator of higher degree than the numerator, we have one horizontal asymptote, y equals 0, and we also have the vertical asymptote at the point 2. So vertical asymptote when x equals 2. Notice that the negative 2 from this bracket doesn't produce a vertical asymptote because that was a common factor. So the negative 2 is just a hole. Next, we may want to find all possible intercepts, so it will be easier for us to graph. And also watch multiplicity of any x-intercept. This will let us know if the graph crosses x-axis or not. If the root is of odd multiplicity, the graph crosses the x-axis. And if the root is of even multiplicity, the graph does not cross the x-axis. So x-intercepts are when y is 0. That means for a fractional form when the numerator is 0. But the numerator is never 0. It's always 1. Therefore, x-intercept is none. What about y-intercept? Well, y-intercept is when x is 0. So if we plug it in x equals 0 to the formula here, we end up with negative 1/2. So y-intercept is negative 1/2. It's also a good idea to check for symmetry if the function is even or odd. Well, this particular function doesn't look like it's even and it's not odd. So recall that to check for symmetry, it's enough to check what's f of negative x, what's negative f of x, and compare it with f of x. And if we get this pair of functions being the same, then the function is even, and if we have this pair of functions the same, then the function is odd. So this is even, this is odd. Well, let's see. F of x is 1 over x minus 2. F of negative x is 1 over negative x minus 2. That's definitely not the same. And to get negative f of x, we can change the negative in the denominator. It will look like 1 over negative x plus 2, which obviously it's neither this nor that. So as a matter of symmetry, there is none. Okay, we have already a lot of information. Maybe we can start graphing, especially the asymptotes. The asymptotes are x-axis, the horizontal one, and x equals 2. It's a vertical line coming through the point 2. We also have a hole at negative 2. Therefore, it's a good idea to check what's f of negative 2, so we can actually place where is this hole. Well, when I plugged in negative 2 to the expression, I have 1 over negative 4, so negative 1/4. Okay, so I know that point negative 2. Okay, so I know that at point negative 2, the value would be negative 1/4, but I need to place a hole somewhere there. We also know the y-intercept, it's negative 1/2, so that's a point that belongs to the graph. Now, to complete the graph without actually graphing calculator, first of all, it's a good idea to recall the general property of a rational. First of all, let's recall that this particular function 1 over x minus 2 can be obtained by using the shape of 1 over x and moving it 2 steps to the right. So the 1 over x would actually look somehow like this, and the other branch like that. So we have the graph already. We know that this graph is similar to 1 over x that is moved 2 steps to the right, except that we have extra hole at the point -2. Now, another step that would help us to understand why the shape is as it is would be to investigate the behavior near the asymptotes. So what's going on with the expression when x is approaching 2, for example, from the right? So if we have numbers that are tiny bit larger than 2, what will happen? We would have denominator that is very, very tiny, nearly 0, but positive. So reciprocal of such number will be very, very high and positive. That's why the graph is running towards positive infinity from the right-hand side of 2. From the left-hand side of 2, if I plug it into this expression, numbers that are a little bit smaller than 2, for example, 199, then I end up with very tiny number close to 0, but negative. That's why the reciprocal of it will actually be negative infinity. So yes, the graph will look like that. And the last step would be to check some additional points if we still need more confirmation. But in this case, it's pretty clear how the graph will look like. And since we already predicted the shape of the graph, now it's a good idea to use your calculator, plug it in the original function, and see if your shape will be the same. Notice that on the calculator you won't be able to see the hole unless you zoom really extensively around this point -2, but it's really hard to see the break because the pixels are so close that they are basically joining this point. So we need to be a little bit wiser than a calculator, and we need to investigate the main feature of an irrational function, such as domain, holes, asymptotes, intercepts, possibly symmetry, possibly some extra points if we want to be more exact, and be able to graph by ourselves. And leave the graphing calculator just to confirm if the graph that you obtain is accurate. If it's not, search for mistake. Okay, we have 2 more equations to graph, 2 more functions to investigate. The first one, if we follow the steps, we're supposed to factor denominator first. So we have x minus 2 times x plus 1. So this time we don't see any holes because there is no common factors. We have no holes. Okay, let's list the domain. Domain of f is all real numbers except for the ones that make denominator 0, so it's 2 and -1. Now asymptotes, since both numerator and denominator are of the same degree, we are taking leading coefficients for the horizontal asymptote, and in this case it's 1. So horizontal asymptote is when y equals 1. Vertical asymptotes come from denominator, so it's x equals 2 and x equals -1. We can easily check that there is no symmetry in this case because of this extra x and -2. And what about x and y intercepts? X-intercept is when the numerator is 0, so when x equals 0. And y-intercept, well, we need to evaluate f of 0. So plug it in 0 everywhere, and yes, we have 0 as well. So x and y intercepts are the same, and they are 0. That means the graph comes through the origin. Well, let's try to graph the horizontal asymptote and the vertical asymptotes. So that comes through 1. Vertical ones are at 2 and at -1. Now the graph comes through the 0, 0 point. Well, in order to complete this graph, I need to know what's going on around the 2 and around -1. So, if x approaches 2 from the positive side, what do we expect? Well, the numerator will go towards 4. The denominator, if this is a little bit larger than 2, this is nearly 0, but positive, times 3, so it's approaching 0 from positive side. So 4 divided by something that is very close to 0 will be positive infinity. So we have f of x approaches positive infinity, which gives us the idea of graphing the shape in this region. It will be from positive infinity going somehow like this. Because we know that the graph needs to follow the asymptotes, but we didn't really know if the graph is positioned in this region or in that bottom region. This is our prediction only. We should actually check a couple more points to be on the safe side. So for example, we could check what f of 3 is. Well, if I plug it in 3, I have 9. Here I have 1 and 4, so 9 quarters. 9 quarters is like 2 1/4. Well, my graph went through 2. It's tiny bit higher, but that's the shape, so we are nearly right. Okay, now in this region, we can graph the shape like that, but who knows, maybe the graph goes like this. So what we need to do is check what's going on if x approaches 2 from the negative side. Then f of x approaches, and let's see, we'll erase this part. This will still go towards 4, but that one will be -0 because you have some numbers that are smaller than 2 minus 2. It goes very close to -0, so this goes towards -0. If 0 can be negative, it's not a -0. It's actually the information that the numbers in the denominator will be very small but negative. So that's why we have arrow rather than equal sign. Okay, therefore 4 divided by something very small negative will be negative infinity. Okay, therefore we know that the shape will definitely go somehow like this. Let's do the same for -1. If x approaches -1 from the positive side, that means by numbers a little bit larger than -1, then the numerator approaches 1 and the denominator, when x is a number that is tiny bit larger than -1, for example -0.99, then this bracket becomes very small positive number, nearly 0 but positive. However, that bracket approaches -3, so this very small positive number times a negative constant approaches 0 from negative side. So f of x actually approaches negative infinity. Therefore, the graph will probably go like this. And finally, if x approaches -1 from the negative side, that means if we have numbers that are tiny bit lower than -1, like -1.1, if we plug it into the formula, the numerator is still going towards 1, denominator is going towards negative constant times a number that is very small but on negative side. So overall it's a positive denominator and very tiny. Okay, so the denominator goes to the 0 from the positive side, and overall function is approaching positive infinity. Okay, therefore the graph in the section below -1 of the domain is in the top corner, not in the bottom. So the graph approaches positive infinity and it goes somehow like this. Now it's a good time to plug it in the formula to the calculator and confirm if the graph really behaves that way. And see this graph, x squared over x squared minus x minus 2. Graph it. Yes, the graph looks exactly the same. It seems like we have a horizontal asymptote at 1. In the following example, we have numerator higher than the denominator, everything is already in a factored form. There's nothing else that we can factor here in real numbers. So we can start with listing domain. The domain of f is actually all real numbers, since the denominator is always positive. This is always bigger than 0 because x squared is always bigger than 0 plus 2. It's definitely bigger than 0. Therefore, we have no problem with domain. We also don't have any holes because there is no common factors to simplify. Therefore, we don't have any holes. No holes. Next, check for asymptotes. Since the numerator is of a higher degree than the denominator, then we can actually perform long division and we may expect a slant asymptote. So let's prepare slant asymptote. How much would this be? Well, x cubed divided by x squared plus 2. So x squared goes into x cubed x times, multiply, subtract. We end up with negative 2x, which is already our remainder because it can't be divided by x squared. Okay, so the quotient is just x. Therefore, the slant asymptote has equation y equals x. And we can graph it on the diagram, somehow like this. Next, let's check our x and y intercepts. For x-intercepts, y is 0. That means the intercept comes from numerator being 0. That means just x equals 0. For y-intercept, we evaluate f of 0, which is still 0. Therefore, the graph comes through the origin. This is the common point for x and y. And finally, we can also check for symmetries. If we calculate f of negative x, which is negative x cubed over negative x squared is the same as x squared, so that's really the same as negative f of x. So f is odd. Knowing that f is odd, it's enough to graph the function to the right of y-axis, and this shape on the right-hand side will be reflected over the origin to the other side. So we have only one asymptote. We have to go through this point. The only option that this could happen is either like this or like that. Well, we need to check which possibility is that. We may want to check some extra points. For example, if I want to know what f of 1 is, plug it in 1 to the expression, it's 1/3. Okay, so now I know that my graph comes through the point 1 and 1/3. So it's somewhere here. Oh, that gives me the reason to believe that the shape will follow that pattern. Well, let's try to graph it. Sooner or later, the graph will try to approach this asymptote. So now this shape, since the function is odd, should be reflected to the other side. So the graph should follow that pattern and then approaches the asymptote. Okay, now it's your time to plug it in the formula to the calculator and confirm the shape of the graph. And here's our graph of x cubed over x squared plus 2. Oh, yes, it looks like it's approaching the diagonal y equals x as asymptote. The curvity around the origin, it's a little bit hard to see. We could zoom in to see it better. Yes, it looks like that. But the general shape confirms our findings. And finally, we have one application problem. A cylindrical soft drink can is to be made so that it will have a volume of 354 milliliters. Let R be the radius of the can in centimeters. So here's our radius. Then the total surface area of the can A in square centimeters is given by the rational function. Wow, we don't have to even develop this formula. It is already given. That's great. Using a graphing calculator, graph A and find R value that produces the minimum surface area of the cone. So we really need to minimize this particular function. Okay, so this is a good time for you to stop the video, plug it in the formula to the graphing calculator, and see how the shape will look like. Then try to figure out what kind of scale to use on the vertical axis, and use the scale as on the diagram up to 10 on the horizontal axis, and graph the shape. So here we have introduced our function 2 pi x cubed plus 708 divided by x. Instead of r we have x. And let's use window to see the shape better. From -10 to 10 it's okay, but for y value I would even go with 2000 so we can see a little bit more of the function. From -2000 to 2000. So, there's a left-hand branch that we didn't even consider because our interest is from 0 to 10 only. But it's a good idea to see overall shape, because if we plug it in the following function that the question suggests, that a goes into 2 pi r square, and graph both of them, you will see that the shape of our function in the long run is really following this curved asymptote, which is a quadratic. Okay, now we can change the window. We can start from 0 maybe, and here also y minimum 0, and 2000, that's okay. So here's the shape. If we want to see only 1000, again change this to 1000. That's the graph. So for example, if we assume the scale on the vertical axis to jump by 100, that will be 100, 200, 300, 500, 700, and that's 900 and 1000. And here's from 1 to 10. This is our r axis, and this is our a of r function. Okay, so I hope that you already graphed on your calculators, and the graph looks somehow like that. Isn't it? And we're supposed to find the minimum point for what kind of r and what is the minimum point. Question A calls just for the r value, the radius of the cone that will produce the minimum surface area. So we need to actually find out this part. So we really need to find the x-coordinate of this lowest point on the diagram. We need to find out this minimum point by using second calc function, minimum number 3, and then scroll the flashing point before the expected minimum, enter after the expected minimum, enter, and approximation, our guess, enter again. Here's the minimum. The r should be around 3.83, and the minimum surface area at this point will be 277 centimeters square. We found that r minimum is approximately 3.83 centimeters. Now for the question, what is the minimum surface area? This time we're looking for the a of r value. That's the minimum value. And it turned out that a minimum is approximately 277 centimeters square. Make sure that you check this on your calculator by yourself. Now explain the meaning of this statement. If r goes towards infinity, so if we're going farther and farther towards infinity, then a of r is going towards 2 pi r square. So the statement really tells us that for large enough r's, the formula for the area, surface area of the cone, is nearly the same as the formula 2 pi r square, which is a quadratic function. How this quadratic function looks like? Well, when we graph it, it will look like parabola, somehow like this. Obviously, I don't have a precise graph here, but the idea is, sooner or later, the graph of our function a is following the pattern of the graph of 2 pi r squared, of the graph of this particular parabola. So here we can see a curve asymptote. So it's not a line, but a curve that the original blue graph is trying to follow in the long run.